Now that we look into the basics of differentiation, let's now look at the derivatives of other functions. So first, we recall we have the inverse trigonometric functions. They are special functions which have specific domains and ranges for them to be considered inverse functions. As we remember, by the horizontal line, tested trigonometric functions are not one-to-one. So we have your inverse sine x until inverse cosecant x. So these are the derivatives of our inverse trigonometric functions. Let u be a differentiable function of x. So this is already in its chain rule form. So just to take note, however, that it's these forms doesn't have a trigonometric form, a trigonometric function, the derivative. Why is that? Let's take a look at the derivative of arc sine x, for example. So how come the derivative of arc sine x is this expression without any derivative? So we know that y is equal to arc sine x. This can be the symbol for arc sine x as well. And the value of y is in between negative pi over 2 to pi over 2. Now, by definition, this means that we're going to have sine y is equal to x. So y is equal to arc sine x means what is that value of x? What is x? Y is the actual input in the sine function, and x is a trigonometric function value. So there. So now, if we're going to find the derivative of this, if we're going to differentiate sine y equals x, this becomes cosine y dy over dx is equal to 1. Dividing both sides by cosine y, we're going to have dy over dx is equal to 1 over cosine y. The thing is, that is y. How did it become something like square root of 1 minus x squared? If you would remember, if our if we're going to have now this illustration of the illustration of that cosine y will come from again our triangle. If this is our angle y with we call this with the hypotenuse of 1, then this is x. Then by the rules of cosine, this becomes 1 minus x squared. If you would remember, by Pythagorean theorem rather, solving for this side, that becomes 1 square root of 1 minus x squared. Now where did this come from? Because sine y equals x. So sine y is the angle here. Y is the angle here, so the opposite side is x, and the hypotenuse is 1. That's why sine y equals x is produced here. So if we're going to find cosine y, we need to find the adjacent side. And by Pythagorean theorem, that's why you get 1 minus x squared. So just to show, this side here, the adjacent side, plus x squared equals what? That's the adjacent side squared. So the square of the adjacent side is 1 minus x squared. So square root. So the adjacent side becomes 1 square root rather of 1 minus x squared. So there. So cosine y becomes this over 1. And that becomes only this. So therefore, by substitution, this becomes 1 over the square root of 1 minus x squared. So the derivative of inverse sine x or arc sine x is this. And since it's a chain rule, the variable x can be a function as well. Hence, that's why it becomes something like this. So that is the reason why for the derivative of inverse trigonometric functions, we do not see rather trigonometric or inverse trigonometric functions there. So let's have a specific example. For example, we have here in number 1 we have y is equal to arc sine 2x. So again, if you recall the derivative of sine, so the derivative of sine, y prime, if y is rather to arc sine u, then y prime will be equal to u prime over square root of 1 minus u squared. Since 2x is our u, and the derivative of derivative of that is 2, this becomes y prime is equal to 2 over the square root of 1 minus 2x. Therefore, we're going to now have 2 over the square root of 1 minus 4x squared. Now, for us to have a rational expression in our function, we multiply the numerator and the denominator by the square root of 1 minus 4x squared. Therefore, the derivative of the function number 1 is 2 square root of 1 minus 4x squared over 1 minus 4x squared. There you go. So let's now have number. So for us to have more complicated examples, let's have number 3 instead. Number 3, we have, let's change it to number 4. So it's more, let's go back to number 2 because it's already signed. So this is a different function that's more complicated. So now we're looking for y is equal to inverse cosine of 1 minus x. What would be the derivative of this? Take note, the derivative of inverse cosine u would be y prime is equal to negative u prime. We'll go negative u prime over square root of 1 minus u squared. In this case, our u is 1 minus x. So the derivative of that would be that negative 1. If that's the derivative of negative x. Therefore, y prime will then be equal to this negative of negative 1 over the square root of 1 minus x squared. This then becomes positive 1 over the square root of 1 minus 2x plus x squared. So simplifying that, simplify that 1 all over the square root of 1 minus 1 plus 2x minus x. It's cancelled, so we're going to get 1 over the square root of 2x minus x. And for us to get a rational denominator, let's multiply both the numerator and denominator by the square root of 2x minus x squared. Therefore, the derivative of inverse cosine 1 minus x would be the square root of 2x minus x squared over 2x minus x squared. So those are examples of finding the derivative of inverse trigonometric functions. The rest are up to you for practice. Now let's go to natural logarithmic functions. Previously, in algebra, we have said that for any logarithmic function, therefore for that includes a natural logarithmic function, we would have y is equal to ln of x, which is equal to the logarithm base e of x, if and only if e raised to y equals x. So that's our algebraic definition of any logarithm, which is applied also to natural logarithm as well. But the natural logarithmic function has its own definition in calculus as well, which is ln of x is equal to the definite integral from 1 to x of 1 over t dt, where x is greater than 0. So although we're not yet in integrals, we were just showing that the definition of the natural logarithmic function is such in calculus. And you're going to talk about integrals later on in future lessons in calculus. With that being said, the definition of e in calculus is the definite integral from 1 to e of 1 over t dt would be equal to 1. In algebra, e is actually the limit of 1 plus 1 over x with x as x approaches infinity. This is just showing that there are different definitions depending on the branch of mathematics, but it's still referring to one and the same. Later on, these laws of logarithms that were discussed before will also be useful in finding our derivative. Now, the derivative of a natural logarithmic function is such. The derivative of ln x is 1 over x. Hence, the derivative of ln u is u prime over u, being u a differentiable function of x. Since the natural logarithm is undefined for negative numbers, it is sometimes written with an absolute value, although sometimes you don't need to. So, for example, we have in number 1, we have y is equal to ln of 2x. So y prime of that would be the derivative of 2x, which is 2 over the original u, which is 2x. So cancelling that, we're still going to get 1 over x. So therefore, the derivative of ln of 2x is still 1, is 1 over x. Now, let's make it a bit more complicated. Let's take a look at number 2. We have f of x is equal to ln of x squared plus 5. So applying the same rule, f prime of x becomes the derivative of the function inside. That's 2x over the original function, that would be x squared plus 1. And since we cannot simplify that anymore, hence the derivative of ln of x squared plus 1 would be 2x over x squared plus 1. And for number 3, we have here y is equal to x times ln x. And that makes it for product rule. Therefore, y prime would then be equal to the derivative of the first, which is 1, times the second, ln x, plus the first times the derivative of the second, which is 1 over x. This gets cancelled, so we're left with 1. Therefore, the derivative of x ln x is equal to ln x plus 1. There you go. The rest of the items here are for your practice. So now that we have the natural logarithm function, we will also have the natural exponential function, which is the inverse of the natural logarithm function. So the natural exponential function definition will use the algebraic definition. Now, the derivative of the natural exponential function is one of the easiest rules to remember, because the derivative of e raised to x is simply e raised to x. And its chain rule version, the derivative of e raised to u, where u is a differentiable function, is e raised to u d prime. So showing that, let's have that in number 1. In number 1, we have y is equal to e raised to 2x. Therefore, y prime would be equal to the derivative of this original one, that's e raised to 2x, times the derivative of 2x, which is 2. So arranging it more properly, therefore, y prime is 2e raised to 2x. Doing it again for, this time let's do it for numbers 3 and 4. So let's do it as first. we have f of x is equal to e raised to negative dx. So it's the same. F prime of x is equal to e raised to negative 3x times the derivative of negative 3x, which is actually, going to think about it, excuse me, becomes negative 3 times 1 over x. And the derivative of 1 over x would be that's negative 3 times negative 1 over x squared. This becomes e over x. Therefore, this becomes e over x squared here. This is u prime already. Since this is negative, I need to write it in the denominator. Therefore, f prime of x is actually equal to 3 over e raised to 3 over x times x squared. There we go. For number 4, we have, I hope it fits, y is equal to e raised to sine x. Following our rule, y prime would become e raised to sine x times it's the derivative of this, which is cosine x. And yeah, that's it. So therefore, y prime is equal to e raised to sine x cosine x. So there you go. The rest of the items are for you to practice. And so so in this video, we talked about the derivative of the inverse trigonometric, natural exponential, and natural logarithmic function.